Hello, everyone. My name is Taqi Abrar, and hello, everyone. My name is Taqi Abrar, and I am from Center for Advanced Robotics at Queen Mary, University of London. Today, we are going to present the interesting work we did in our lab. But before this, let me introduce you with my team, uh, Daniel Khalil, and then we have got Ahmad Hassan, and we have got another fellow, Tayyib Ansari. And this lab is managed by Professor Kasper Altufa. And what we are going to do is we're going to show you a few interesting robots and interesting things that uh, are very useful. Starting from an eversion robot, it is called a growing robot, and it can grow, and it can bend, and it can go to the places which are not accessible by normal human. Another thing to tell you is this robot.
Ask them if element is live.
Uh, just one more thing. So this robot is actually made from fabric, and it has got no motors and anything complicated circuitry in it, and that's a good thing. So it is made from fabric, and it's use air to operate. So it use air to grow and air to bend and to go to the places which a normal human cannot go. So what I'm going to show you is show you the robot, how it bends, how it grows. So let's go to the robot and see how it works.
You can start.
Okay, so the first robot we're going to show you is a Aversion Robot. This robot is a robot that can grow in length, and it does this through pneumatic power pressure. This robot as we can see, it can be made from fabric or can be made from plastic sheeting. This robot is, as you can see, it is growing in length using pneumatic pressure. As the pressure goes in, as the air goes into the robot extends in length and grows. This is its way of actuating itself and its way of moving. And in doing so, it can move through tight and narrow constrictions in its environment. This robot is able to, due to its soft structured body, this robot is able to navigate through narrow and tight constrictions by deforming its soft body. This robot is also able to bend in different ways, and for example, it can bend left and right using different mechanisms, which we'll show you in a second. As you can see, as my colleagues are extending the robot, and the robot is growing in length, and it resembles a vine plant, which also grows in length from its tip. As you can see, this robot is bending, and its method of bending is through a pouch mechanism system. So the pouches are like pockets which we can fill with air, and they can contract. So if you have pouches on the left-hand side, for example, and you have pouches on the right-hand side, and you fill the pouches on the left-hand side with air, they contract, and that allows the robot to bend in the desired direction. The pouch, and in doing so, it acts in an antagonistic way, as one set of pouches contracts while the other one relaxes. This bending can be in the horizontal direction or the vertical direction, allowing us to be able to achieve multiple degrees of freedom and to reach places that a normal robotic arm cannot reach. Okay, so the next robot we're going to show you, next set of robots we're going to show you are also Aversion robots, but these robots are instead of being land-based use, are going to be for underwater use and also in air use, so flying Aversion robots instead. So if you just bear with us for a second. So the nature of Aversion robots is that they can be applied in many different environments. We apply them. So the robot that we showed you was applied to going under buildings, going under the buildings to inspect their foundations. But we also develop robots that are able to operate underwater, for example, in coral reefs, and also in inspecting oil platforms and oil rigs and wind turbines and that kind of infrastructure as well, and also shipwrecks. The special nature of Aversion robots allows us to do this because of its non-destructive mechanisms, non-destructive method of moving. So also we develop robots, these Aversion robots for flying applications as well. We pump them with helium, and that allows us to be able to enable them to float in air. So we're just about to go and show you our underwater Aversion robot. Okay, so as you can see, we have an Aversion robot in the tank. This one is also a fabric Aversion robot. And what we're going to do is we're going to show you growing in length. So as we pump water inside instead of air this time, you can see the robot extending in length. As you can see, it does this with ease, and it's able to grow through the underwater environment in a non-destructive manner. The next robot we're going to show you is a flying eversion robot. This robot is able to this robot is able to be able to pump with air or helium, and it's able to float in midair. So what I'm demonstrating now is the robot extending in length. So as you can see, we've shown two robots made out of eversion robots made out of fabric, and two eversion robots made out of plastic. As you can see, the eversion robot is extending in length and growing from a base point all the way up to its tip. And as you can see, it was able to float in. It's able to float in midair. This robot is made out of a polythene plastic, whereas the other two robots that we just showed you were made out of fabric sheets. So as you can see, these robots can be made from a variety of different materials and can be constructed from very cheaply. This is one of the advantageous points for developing these kind of robots. The next. It's very low cost to make these robots. As you can see, it's made from traditional house materials such as this Tupperware box and this very thin plastic sheeting, and that's one of the advantageous points of applying these robots and developing these robots. So the next robot that we're going to discuss with you and show you is our robot gripper, made from fabric, and that uses the same principle, the same eversion principle that we've been discussing. This robot can pick up objects that are, and it's very impressive because it can pick up objects that are very heavy. So these are also based on the eversion principle, but are in gripper format. They are made of fabric as well, but these ones are also inflated using pneumatics. We do this using a pneumatic regulator, which my colleague is going to demonstrate now. So these robots are, as you can see, have got two that are, instead of having a single eversion chamber, it's got two eversion chambers on either side.
So you can see this gripper, and it's made from fabric, and it's again very lightweight and low cost, and it's use only air for work. And here you can see a small demonstration of this gripper grasping a bottle, and with very low air pressure it can work. It can hold different objects, it can grasp, and the thing is it's very lightweight, flexible, so it won't harm or destroy anything. It's very safe. Another advantage of this is you can, or not only grasp, but it can also use for pinching of different objects as well. And but the main idea of all these prototypes we have shown you, like Aversion Robot, underwater, in the air, on the ground, and this now eversion based gripper, the aim is actually to use and construct a robot that is useful for human, that can work with human. And the main idea is used for this is to make a small gripper hand, a prosthetic hand, and for the people who cannot use their hand, and to make a gripper from fabric which can be used. So the final aim and the main prototype, or the main aim end goal, is to make something like this. There's a small prototype of a prosthetic hand that we are going to use, and the aim is to make it from fabric and use pneumatics to work on it. So you can see that it is a very small gripper, and it's very small, and you can see it is very flexible as well. And the idea is to use these materials and to construct something that is very helpful for human. and make a prosthetic arm from fabric that use pneumatics to work. And you can see this is a small uh, finger working, and that's how, so use all these technologies that we have shown you to come to this end goal and make a small prosthetic end like this. It is made by one of our colleague Jan Frost. So to make something like this that can be very helpful for the human and that can work with the human, because the gripper that are commonly available either are made from rigid materials or that are heavy or bulky, which is not safe for human robot interaction. So made something from the technology that we previously show you to come to this end goal. And this allows us, for the person operating is to go to the places which are not accessible by human, and ensuring the safety of the environment. So this is the end goal of all the technologies that we show you, and that's all from our side. And if you have any question, please feel free to ask. And yep, so these are the prototypes that me and my colleagues would like to show you, and I've shown you all these prototypes like Eversion Robot growing on the ground, underwater, in the air. And then from this Eversion principle and fabric based structures, we move to fabric based gripper, and then to come to the point where we are aiming to go for prosthetic hand. So if you have any question, please feel free to ask. Thank you. Any question, please feel free to ask. So let me just reiterate. We showed you Eversion robot made from fabric, and it's a long robot that can grow and it can bend and can go to places which are not accessible by a normal human. Then from there on the ground robot, we move to a robot, Eversion robot that grows underwater, and then it can also grow in the air as well. We use this concept to make a small gripper for the human so they can use this gripper to reach the places which are not accessible by a normal human, and it's also very soft and flexible. And then from there we move on to show you a prosthetic hand, like what's the main aim and the main idea of all these technologies.
to be able to use this robot to explore coral reefs in a non-destructive way and even archaeological discoveries underwater. Yep, and also to visualize and observe marine life in its natural habitat without causing any destruction to the marine environment. We hope. Yep. So these robots can move through spaces that are inaccessible to humans. For example, moving underneath buildings, moving in lots of different ways. And yes, and it can be used in extreme environments. Yep. So extreme environments we're looking into is including in the nuclear industry. So to go through to navigate through nuclear reactor pipelines, and also for navigating through collapsed buildings when an earthquake has occurred, and also in disarming underwater mines. If we look at the application of underwater mines, these robots' motion, in that it grows through its environment, and that's its movement mechanism, allows us to be able to move close to the mines without causing the mines to explode. And in doing so, we can classify the mine and find the appropriate way to have it safely destroyed and disposed of. The next robot we're going to show you is an aversion-based gripper. Oh, sorry, a prosthetic hand. We hope that one day this prosthetic hands can be used for rehabilitation purposes and also for amputee victims. This robot is soft in structure and can be and in its current prototype form could be used for a small child's hand. The soft materials allow us to reduce the amount of control complexity in the robot, and also allows us to build the robot from relatively cheap materials, allowing us to make it easier for children to and children and adults with who are amputees to receive a prosthetic hand. The hand itself is pneumatically actuated and is formed from rubber and pieces. Having a pneumatic actuator can be heavy. However, we hope that one day it can be minimized to allow us to have it mounted on a human body. This robot could potentially also be actuated in other ways, for example, using water, but this will be heavy, which is why we have opted for using air. As you can see, the robot is made from cheap materials that are flexible and are stretchable. They are also very durable. So having, for example, for children, it can make it much more sturdy and allow us to and allow the children to have movement in there, to have a hand that they can interact with the environment with. As you can see, the hand is quite small, but we hope that as the child grows up, the child can have this prosthetic hand replaced with bigger, larger hands as they grow up that are anthropomorphically adjusted to their body, so that basically it matches their other hand if they have another hand, or matches the rest of their forearm or their remaining arm that's left over after their amputation, or if they were born without a arm or hand. And this would allow us to, because of the robot's soft materials, the hand can be cheaply manufactured. As you can see, it's very flexible and very deformable, like our hands. So if you think about our hands are deformable and they're soft in structure. They've got a rigid skeleton inside, but it's soft to the touch. Just like our hands, this robot has got it's actually completely soft, but it can be rigid when you want it to be, using pneumatic actuation, using air. This robot is, as you can see, it resembles a human hand in that it has 4 fingers and a thumb. All of them are posable and can allow a greater amount of movement in someone in the amputee's hand, prosthetic hand. As you can see, the different parts of the hand can be individually controlled, and this allows the person to have a greater reach of motion. So if you have any questions, please write them in the chat or speak them aloud, and we'll be happy to answer your questions. Yep, so the idea is to make a prosthetic base gripper from this prosthetic hand. As you saw, our other Aversion robots were able to extend in length. And we hope that by using the Aversion principle, which is to grow in length, we can we can create a hand that's able to, where the things are able to grow and grasp an object by growing. And in doing so, hopefully it can interact with the environment in a non-destructive way and be manufactured from cheap materials that we can easily manufacture and make it cheaper and easier to allow people to have prosthetic hands. We have developed these aversion based grippers. Our current aversion based grippers are fabric based, and that allows us to have more durability than the plastic sheet based aversion robots, which are fairly thin and flimsy. And by having this durable nature of this material, it can last the human longer, because human activities can vary in depend on what types of strengths they apply to the environment or what type of things they pick up. And by having this durable material, it allows us to have a greater amount, be able to exert a greater amount of force on the environment, but also being able to, while still maintaining a soft touch. One day potentially we could even implement a sensors into the robot prosthetic hand, aversion based hand, where they could sense their environment, which, and due to the soft nature, it allows us to have simpler control. Current rigid robot prosthetic hands are expensive to manufacture due to their rigid structure and due to their and their rigid structure enables the controller, unfortunately, enables the control algorithms to be very complex. By having these soft hands, they enable us to reduce the level of control that we have in the environment, and also to interact with the environment in a non-destructive way and more in a human-like way. I'll just pass you on to my colleague.
Thank you, Daniel. We've got a first question that how far is it from commercialization? So from Alia, I'm gonna ask which robot are you talking about? The growing aversion robot, the or the soft prosthetic hand? Can you please specify which robot are you talking about? The hand. So I'll let Taki Abrar, my colleague, to answer that.
It's not that far. As you have seen, like we have got fabric-based gripper and a small prosthetic hand as well, and they all are working very fine. These gripper can use to grasp objects and to hold them. They can use to lift some weight as well. So it requires industrial help from the industry as well, because as a researcher in the lab we can make these small prototypes, but now it's up to the industry and those industrialists to what they think of this. These are very lightweight and soft, and we have demonstrated this hand by Jan Frass, one of our PhD colleague, several times in several different exhibitions, and it worked very well. And here we showed you only the working, but in the lab, we have also integrated some leap sensors as well. So with these sensors, it can imitate the hand movement as well. So it's not like you are using commands, but it can also go use follow the orders as well. Like if someone is grasping, it can also grasp. So it's like master and slave combination. So it can also imitate the movement of human hand, real time, as you can say. And it's also very viable as well, and it's low cost. And the thing is, if it's attached to a human body, as the body grows, the size of the hand also grows. So you can also replace this small hand with a bigger hand, and the principle and the working will remain the same. I hope this answers your question. And to further add, let me.
Yep. So I think to further add to that, I think there'll be three things that would be needed to commercialize this product. It's already using cheap materials, which is fantastic because that allows us to allow us to apply it more widely and to reach more people. But I think what it will need is to integrate it with something called electromyography signals, which are generated by our bodies, and that would allow us to read the signals from the human, the rest of the arm that's left over, the residual arm that's left over, and be able to transmit it to the hand so that the human can operate and control the hand using their existing electrical signals. Another thing that I think it would need is sensors, so it can detect tactile objects that it picks up, which it currently does not possess, but I'm sure that could be integrated quite easily due to its soft structured nature. And I think the third thing that needs to be investigated before it's commercialized would be the materials that it's manufactured from, as they would need to be durable and long lasting for a human to use it, and should not be replaced, and would need to last a considerable amount of time before it needs to be replaced. And
The second question: have you started integration with these with the sensor?
Sensor. Okay, so far what we have achieved in the lab is a use leap motion sensor with this prosthetic hand, and with another hand, we another our colleague is using EMG sensors as well. So we are integrating sensors, but it's not fully integrated. As you can see here, we don't show you the leap motion sensor, and but later we are trying to uh, integrate all sort of sensor that can not only replicate the movement but also can sense. And because for gripping you require force sensors as well, so like how much force it's exerting on an object to grasp or hold it. So yes, so the later idea uh, is to integrate several sensors at the fingertips, so we can get more data and we can use it properly. Yep. Yep. And if I hope this answers your question. And yep. Any suggestion from anyone is also welcome. So let me reiterate what we have shown you so far. So we have shown a very big growing eversion robot that can grow in length. This robot grows on the ground, and it can go to the places which are not accessible by a normal human. But this robot can bend left, right, and it can also grow vertically upward as well. The idea is to use this robot for several applications like extreme environments, search and rescue, and navigation, or to a place which is not seen by human. From there, we showed you another prototype, another version of this version robot that not only grows on the ground, but it can grow underwater as well. So this robot can be used for research in marine life. And then we showed you another prototype of a version robot that grows in the air. And what we try to show you is, like, we use very soft and low cost material to construct these robots, and they are very useful in several applications like extreme environments. From there, we move to grippers as well. And initially, we show you an eversion based gripper. So, what we want is to a gripper that can grow and then grasp, just like human arm, that it reaches an object and then it grasps an object. So similarly, fingers that grows and then grasp. And we show you a fabric based gripper. And then the end goal is to use all these soft technologies like eversion and soft materials to construct a prosthetic hand, the for human, that can grow, and it can be used by human to to perform daily life of applications or work. And we show you a small prosthetic hand made from rubber actually, but it's not everting. So the later idea is to introduce eversion in these types of hands, so to reduce the size, make them very lightweight and soft. And this prosthetic hand from rubber, you have seen, like, it has got similar function and similar structure as a human arm, 5 fingers, and working similar to the human hand. And they can also grasp different objects. And you can see it's very small, but later, if the human grows, so you can just replace this small palm, and then you can use a bigger palm, and the working principle and the operation will remain the same. uh, Let me tell you, like, in the lab, what we have done is, we have leap motion sensor that can imitate human hand, and then transfer this movement to this robot, and it works similar what you are doing and what a normal human do. And in another arm, we have got EMG sensors that uses human signal, and they can work accordingly. So these are all the technologies that we have, or we are using in the lab. It's ARQ, Center for Advanced Robotics at Queen Mary, and Professor Kasper also is the head of this lab. And my name is Taqi Abrar, and on my left is Ahmed Hassan, and on my right is Daniel Mahmoud. And we all are PhD students, and we are working on different projects. I'm working on eversion based robot on the ground, and Daniel is working on eversion robots in the underwater and in the air, while Ahmed Hassan is working on fabric based gripper, and he's also introducing eversion in these grippers. If you have any question, please feel free to ask, and you can write your question in the chat box. Thank you.
Okay, so we've got a question over here.
So we have another question. It says, "What do you do if the growing robot gets a puncture?" Very interesting question. And the thing of the advantage actually of eversion-based robot is, even if they got punctured, they work, because the air pushes the the material which is inside, and the robot grows. Even with a puncture, these robots grow, and they perform the work they are meant to do. Even but the efficiency can be low and decrease, but they are capable of doing work even they are punctured. A small puncture cannot affect the robot's task, and the robot can perform the task that is given to the robot, and it can even grow with a puncture as well. And we have tested this in our labs and outside the lab as well. Like, even with a puncture, a small puncture, the robot grows and grows, and it can bend and grow again.
So even if it has a puncture, some people in academia use the puncture to an advantage. So if they don't have a pressure regulator, which we are very fortunate to have and afford, so what they do is, instead of having a pressure regulator, they have like a small hole in their Aversion robot, so they're still able to extend and grow their Aversion robot with a puncture. And the puncture regulates the amount of air that's flowing through the robot. And they can control the extension by the punctures in the robot surface. So a puncture is not always a bad thing. If you want to reduce the amount of the amount of force the robot generates, a puncture might actually be beneficial to you. Thank you for your question. If you have any further follow-up question or just another question on something else, please feel free to ask. So yeah, in the meantime, while we wait for questions, so my work on underwater aversion robots for exploring coral reefs. The reason why that's really important is because 90% of coral reefs, the internal structure of coral reefs, has not been explored, and that can unlock so many. And if by using these robots, they can unlock so many new research and new scientific knowledge that we never had before. So these robots are able to move through through a tight and narrow and confined spaces with ease through growing, and in doing so, it can move in a non-destructive manner. By moving in a non-destructive manner, it can prevent damage to the coral reef and the organisms that inhabit it, allowing us to move through the coral reef without destroying it, and be able to learn scientific knowledge about coral reefs that we didn't know before. This is hugely advantageous compared to current methods of exploring coral reefs, which can be quite destructive. So it looks quite promising. One thing that is quite interesting in an underwater environment compared to other based environments, such as such as on the ground, because air is very similar to on the surface of in air as well. Water and air are very similar environments in that we have a three-dimensional environment, unlike on the ground. So my work is to look at the motion control of these robots. So these robots, there are 4 different types of motion control that I look into: is growing, shrinking, changing in altitude or depth if it's underwater, altitude if it's in air. So it's changing in height that the robot is floating at, or steering, which can be left or right. As you saw, our bigger version robot was using a pouch mechanism as its steering mechanism to turn left and right. And the pouches are basically pockets, which we can fill with air. And that allows us to be able to bend in a certain direction. So if you had pouches on the left hand and the right hand side, and you inflated the pouches on the left hand side, those pouches contract, and that allows that enables the robot to bend to the left as the pouches are contracting on the left hand side, while the right hand pouches are deflated. These pouches are integrated into the robot's body, and it has been shown that by integrating them into the robot's body rather than having them externally situated on the robot, we can achieve 90% more bending. This is hugely advantageous for moving through environments that are unknown to us and achieve high degrees of bending. As I've already mentioned before, these robots are also capable of having infinite degrees of freedom at each point. And also another method of actuating these robots is by having zero actuation at all, and just using the environment and the robot hitting the environment to enable it to move through the environment. This can be advantageous in certain situations where where the environment is unknown to you, and you just want to go through the environment in a randomized way. Steering mechanisms can also be useful when you know the direction when you want to go in a certain particular direction. Yep, and these robots can be applied in so many different environments and in so many different applications. Areas of interest of these robots could potentially be in space exploration due to their cheap costs to manufacture, their lightweight to send them up into space, and their soft structure so that we can examine objects and space debris potentially, or even go onto other planets and explore the planet without causing causing damage to that planet or to that rock face that we're going through, and get a better picture of the stellar and sorry the planetary environment. My work on underwater robots, which I was mentioning earlier, looks into filling the robot with. It looks into changing, as I was saying, changing the depth of the robot that the robot floats at. So what? And I've also been exploring that for robots that can also fly. So for the robots that can fly, I've been exploring using a ratio between of helium and air, and by changing the amounts of helium and air in the robot, change the height that the robot floats at. In water, it's a bit more complex because we have something called Boyle's law, which prevents us from, which means that if we pump the same amount of let's say air at one point in the ocean, the deeper you go, the more the pressure reacts on the robot's body and causes it to be compressed. So it's not a one-to-one solution. So it's not a transferable solution from air to water. So we're currently thinking about different ways we can enable the robot to change its depth underwater. These robots can have multiple. So aversion robots, as we've shown today, most of the aversion robots we showed today had a single chamber. That means that it could only grow in length. But a lot of these robots can also have multiple chambers that can enable it to achieve bending, and also depth control. And the fabric based grippers that we showed today also are quite interesting as well, because they have the ability to grow and to grasp objects. And they use something, and all our these particular robots, let's talk about that first, are they're fabric based, but they also use a pleat like structure, and that enables them to bend in a curved way. The robots we were shown today have been manufactured. Well, the fabric-based robots we were shown today have been manufactured using a sewing machine, and the air-based ones, so the air-based fabric robots, have got, of course, fabric puts holes sewing will put holes in the fabric. So to counteract that, because air molecules are quite small, so it can easily go through the holes made in the fabric, we use vinyl strips that we heat press onto the robot's body, and that allows us to be able to keep the robot to make the robot airtight. For the water-based robot, for the underwater robot, having holes is actually very advantageous, because it allows us to be able to remove the excess air that's trapped inside the robot's body, and that enables us to be able to have further control over the robot, as we can enable it to achieve depth without having excess oxygen inside the robot, which will prevent it from which will make it bend upwards towards the sky. The other robot that we showed, which was manufactured from the other version robot that we showed, which was manufactured from polythene plastic, is manufactured using regular shirt iron. So that robot is manufactured using very, very cheap material, and actually so it uses a dust sheet. So what we do is we cut a sheet of we cut a little rectangle from the dust sheet. Let's say it's 1 meter long and 10 centimeters in diameter, let's say. We then take two pieces of sheets of paper, of A4 paper. We put one on the underneath of the side of the robot. We fold it over. We put it on one side of the robot, and we put the other sheet on top of the plastic robot. And then we use a normal shirt iron that you would use for ironing your shirts, and we'd rub it along the paper that's on top of the robot. And in doing so, it heat seals the robot, allowing us to create an airtight seal. And this airtight seal enables us to avert the robot without air escaping. What we've also shown today is two different types of actuation methods. One of them has been hydraulic based, which is water based. So we fill the robot with water, and it allows us to extend using water, and also allows us to achieve a neutral buoyancy underwater. So that allows us to stay underwater without the robot floating up or down. Yep, please.
What has been the biggest challenge you have encountered while doing this research?
Yep, so that's a very good question. So one challenge when doing this research is mathematical modeling. So because these robots have so much movement in them, it is very, very difficult to model and control. Well, not control, but to model them mathematically. So what I mean by that is, uh, by mathematically modeling these robots, we can develop control methodologies that make it easier to control them. But due to their soft structure and their infinite degrees of freedom, that makes it very difficult. So that's one of the challenges. The other challenges is that I come from a traditional robot making background, whereas these are fabric-based robots and plastic-based robots. So their manufacturing is very, very different to what I was used to. So it took a bit of learning, learning how to sew and things like that. But I had some really good teachers, and that made the learning process much easier. And once you it's pretty straightforward to get the hang of, because I don't do any complex sewing, for example. So you can get it within 1 week, and you'll be fine to create robots of your own. Another challenge I would say I've encountered would be to test these robots in different environments, because our lab facilities at QML are very good. However, our underwater tank is quite small, so thinking about proportioning the robot to fit in certain environments has been a challenge as well. I'll pass you on to my colleagues to discuss their challenges as well.
Thank you, Daniel. There are a lot of challenges, because it's an ongoing research. So, as you've seen, those long growing robots and using just air, they can grow and they can bend. The main challenge is, to again, fold them back to their initial state. So when you supply the air, they grows, but if you stop supplying the air, they won't come back. And that's the main challenge, and we are still working on it. Uh, Regarding this, we are also testing several mechanisms, not for the big growing robot, but the small eversion based grippers. We are testing few mechanism to grow and then to fold the finger back inward. And we are pretty much successful in doing this, and we have submitted tested few mechanism that can fold it back the finger. So when you supply the air, they grow and they can bend and they can grasp an object. But if you cut the air and if you don't supply any input, they can just come back to their initial position, which is very short. So the advantage of eversion is, from very small size they can grow to very large size, as you have seen in the robot. And the another advantage is it's a very less friction as compared to other types of motion. So if you consider sliding something, you can imagine how much friction it can have if you slide something on the ground. But with eversion, it's very less, because the thing is the material that's growing, it actually comes from the inside and just comes outside and it don't move. We have seen the robot that the part that is grows, it just stays and only the tip is moving. When we inflate the pouches, it can turn left and right, and if you supply the air to the main chamber, it just grows. And once it's grown, it just stays, the body stays at the tip, just like a plant vine. It just replicates the movement of a plant vine. So when you supply the air, it just stays and it won't move, and only the tips grows and it moves, and only the section that you want to move, you inflate that section, as my colleague mentioned about the pouches. So we've got pouches, and when they are inflated, only that section moves. The rest of the eversion robot's body stays. So that's also another advantage. And we have implemented this this bending techniques in several other types of robot as well. and one application is an eversion based gripper that we are working on it. It's again made from fabric, very lightweight, very low cost, very flexible and soft in nature. And so the idea is, instead of moving the whole system, whole robotic system and the arm towards an object, why not just grow the finger towards an object and then grasp it? So with this idea, we have built this eversion based grippers as well. And so far we have made it from fabric, and we are working on it, and we have successfully implemented this folding back mechanism as well. So if you don't supply the air, the finger will come back to its initial very small state, where the size is very small, and where you supply some air, they will grow and they can extend and they can bend, and they can work similar to a human arm.
We
And
have a question that can we use the shared memory thing to pull the actuator or the robotic growing robot back?
okay, so we have a question about shape memory and implementing it on the robot. Yes, we can. There is no doubt we cannot implement. Yes, we can implement, but the thing is the response time. So as we you can see in the videos of the Aversion robot, the response time of our robot with the pneumatic is very high, and it's very quick in response. But with the shape memories technique, the response time is very low because it takes time to change its states. So because of this, we move from shape memory to uh, pneumatics, and it's more, the time response is very quick. And again, the safety, because what we want is to use it with the human, and we don't want anything that is thermal or electric to be integrated with the human, even though there can safety measures can be taken, but we want it to be very very safe. And for this, we are using pneumatics, so you can see if there is all around us. So and the thing is, the pressure we are using are less than 1 bar. It's very low pressure that we are using to operate our devices. So we are making them very soft, and not very complex mechanism we are using in our robots. So if we try to teach about our robot to the people, so they can understand, like air and everything. So we supply the air and it grows, and it's very very simple techniques we are using to operate our robots. But yes, we can implement several other techniques, including shape memory and even motorized system and tendons, where we pull the tendons or rope and it can bend. We can implement, but there are difficulties and safety concerns, and not only safety, but there are also challenges as well. So with the pneumatics, we overcome all these challenges and safety concerns. To That's why we use pneumatics. So there's only one system for the whole robot, and you can see we showed you several prototypes: eversion robot on the ground, eversion robot in the air, eversion robot inside the under the water, eversion based gripper, and prosthetics, and all using same pneumatics. And you can clearly see like how simple pneumatics is, and how easily can pneumatics can be implemented on different robots, and it can be used in several applications. And if you have any other question, please feel free to ask.
I think we only got 10 minutes for the live feed, and
Uh,
then we're gonna finish
uh,
at 5:30.
just to remind you, like we have got only 10 minutes left for this live feed. So if you have any question, please write in the chat box so we can answer your query. And if you need any further description, or if you want any further details of the robot, just let us know so we can describe our robot and we'll show you.
And if you want to see the demos again, they are at the beginning of the
Uh,
video and halfway
um,
through.
so, and just one more thing. So, we showed you a few demos, like eversion robot on the ground, in the water, on the space, and grippers, a prosthetic hand. If you want to show them again, you can just move to the beginning of the video, and in the middle of the video, we showed these prototypes twice in the video. So, if you want to show, if you want to see those prototypes, you can just scroll down to the very beginning of these videos, and you can see those prototypes. And yep, if you have any question, please feel free to write them in the chat box so we can answer them. Thank you. want to tell you something about the robot?
Yeah, okay, sure. Yep. So I'll talk a bit about the frictionless movement of aversion robots. As my colleague said, as the robot's body material grows, the internal body material becomes the external body material as it grows, and this allows it to grow and move in a frictionless way. And by moving in a frictionless way, it causes no damage to its environment. That is such an important thing, as pretty much any single robot, every single other robot that our group develops creates friction with its environment. So this is one of the only robots that creates no friction with its environment, and that allows us to be able to move in environments that we wouldn't normally be able to do, such as like fragile environments. We listed a whole host of other environments that they can be applied to. Those include archaeological digs, coral reefs, underneath buildings during earthquakes, and a whole host of other applications that require delicate and precise control and the ability to prevent damage from occurring. One also quite interesting thing is that we've shown that using hydraulic and using water and air-based robots for moving. A lot of these robots, traditional robots, will be powered using something like a DC motor, which is electronics powered, whereas our methods use water and air to move. There's also these by using these kind of substances rather than electricity and current, we can enable these robots to be applied to more harsher environments and have them being more durable in these environments. These include being in nuclear environments where we need to be quite careful with using electronic equipment that could get damaged in these environments, but also by applying using pneumatics in space and using these soft robots in space, it can reduce the cost of sending robots into space, and because of their compressible nature of these aversion robots, they can be we can send more of these robots into space, allowing us to maximize the amount of robots we can send up into space, making it cheaper to send them up into space. Yep. So these So as we showed, we show loads of different applications that our team develops for these aversion robots. They're based on vine plants. So vine plants also so they're biologically inspired in that they grow from the tip of the robot, which is the very front, and their tip continually changes, as you saw. So it starts off quite close to the robot, where it starts off in a compressed shrink state, and then grows outwards. And this growing motion is non-destructive and frictionless. So these robots, the movement is completely unique in that it grows through movement. There are lots of different other types of inflatable robots, but these robots are certainly unique in that they have their growing abilities. And we've discussed lots of different ways of manufacturing these robots and the materials they're manufactured from. Things that would be interesting to investigate one day would be semi-rigid structures of these robots to make these robots rigid at certain points. And we've discussed different ways of actuating this robot, including using pouches. My colleague mentioned using tendons as well, tendon-driven actuation, and also using and also potentially using control chambers and locks, which is where you would have locks where we can lock the different sections using small little mechanical clips. Each of them have their own advantages and disadvantages, but we always keep an open mind and are always willing to try new things. One thing that we recently worked on as part of one of our Aversion Robot projects was developing a cap that would be able to deliver a payload. So one of these very important aspects of an Aversion robot is its ability to deliver a payload to a constricted environment, and even be able to retrieve a sample from that environment. So one of our projects recently looked at developing this tip cap, and we developed so many different types of these caps that would stay at the Aversion robot's front at its tip, and we'll be able to move with the Aversion robot as it grew in length. So we investigated using magnets, and we investigated using the pressure from the walls of the robot, and we investigated many different mechanisms, and we finally came up with a really nice way of doing that for one of our 20-meter long robots, and that involved having the pressure from the robot's body expand inside this hollow tube-like structure, and we were able to mount a camera to the tip, which we were able to use, perform visual inspections inside a narrow environment. And we were in this test. We were simulating it going underneath a building to explore the foundations of a building. And that project was also looking into potentially even fitting a insulation machine to make it cheaper to insulate people's homes. And that's something we were looking at implementing onto our tip cap. So payload delivery is a very important aspect of an Aversion robot, as well as steering and compressing into and retracting into a smaller state, and extension and altitude / depth control. They're all very important aspects that we are looking into developing further. We are also, as we said, we're currently investigating using plastic sheeting and fabric-based robots, but we're open to the idea of looking into smart materials and smart polymers that are able to change shape and able to move using this averting mechanism. Yeah. If you have any, sorry. Yep.
Okay, so just before the ending, so it's like time. We conclude our this transmission. First, I would like to thank all of you, UK Robotics, and my colleagues as well, Ahmed Hassan and Daniel, and for their support as well for this good transmission. And so just to conclude, so we showed you few prototypes of eversion-based soft robots, and they are made from fabric and plastic, and one of the prototypes was of prosthetic hand is made from rubber. Eversion-based robot can grow on the ground, they can grow underwater, in the space, and if you can see on the left of your screen, you can see a small prototype of the wall. And here we are also exploring, eversion robots, a vertical growing capability where they can grow between the voids of the wall. And we also showed you eversion based gripper, and we also show you a prosthetic hand. That's the end goal for all these technologies. That's all from our side. If you have any question, you can always come back to us. And just ending this, let me tell you one thing. If you, as we mentioned, like it's very frictionless, and we don't have any friction. If you want to feel how eversion robot grow, so I can just give you one small demo. Can I have this? So you can use this, and you can also feel how this eversion robot is actually work. So compared to other technology where we talk about sliding, you can just slide this thing on your hand, and you can feel how sliding works. You can roll it objects, and you can feel the friction and how it's moving. But if you want to feel how eversion works, you can just just put your finger, and you don't feel anything except a small touch. So that's how eversion works with respect to the environment. So it's not sliding or rolling. It just it's coming out from the inside, growing and just stretching, and it's staying there. That's how eversion works. And you can also test it, like how much the friction can be. So it's very negligible or zero. And that's all from and our the link of our research group is in the chat. You can always contact us. And we are students from Queen Mary University of London. Our lab is Center for Advanced Robotics at Queen Mary, ERQ. And thank you for your time. And if you have any question, you can always come back to us. And the link of our lab is in the chat. Thank you.
Thank you very much.
Thank you.
Thank you.
Bye.
Bye.